It is extremely rare to have a planet where there is soil. As this living crust that is smeared over the surface of our planet. Most of the planet is not living. It's mineral, it's never known life. It's just this rock. And yet soil starts forming on it and creates this crust, this very thin layer where life is possible. This is where it all starts. Right here from the glacier that has been scouring the rock, grinding it to a fine dust, pulling out the nutrients, releasing them into this water that comes from right under the glacier. There is no organic material in this. This is mineral, beautiful in color and beautiful to feel on your hands. It really is the beginning of the soil. This rock has been ground to such a fine texture that it remains suspended in the water. They will remain suspended for such a long time that they will manage to get all the way to the sea. Soil supports me on this precarious ledge where we can see life gaining upon the mineral basis of the planet, the nutrients of the rock being transferred into the living layer that is the soil that supports then plant and other life, and building up life to make soil thicker and thicker as life complexes upon itself. This type of material you get in your garden when you buy peat moss, the famous sphagnum moss, the one that holds mammoths and all kinds of things, like in a huge refrigerator, without decomposing. This sphagnum moss produces acid that keeps things from breaking down, from decomposing. Very exciting to be putting your hands into very old carbon that was accumulated here by photosynthesis. We can go down thousands of years in this. That could be tens of meters deep. This has no mineral, no rock, no clay, no sand. It's just living things growing on themselves. Soil that is completely biological. Here, water and land are having a dialogue of nutrients. The nutrients that were in the water are being pulled out by the waves, the wind, currents, but also by the uplifting of the land. The coral that trapped the nutrients from the ocean is coming up here at the edge and making all these nutrients available back for terrestrial ecosystems. These corals have trapped carbon in the form of CO2 that was dissolved in the water, as well as calcium, which is a very important nutrient for plant life. and has made it into solid skeletons that form the body of the coral reef. And as it becomes smaller and smaller, thinner and thinner, becomes sand, one of the three important elements of soil. After soils are born, they have a life, and we can see that life develop in places like Hawaii, where each island was formed at a different time.
What makes Hawaii such a great place to study and understand soils is, first of all, the volcano. You can go from places where the volcano is active and the rock was hot yesterday to places where you have soils being affected by life for 5 million years.
The Kilauea Iki, the small crater, is on the other side of the cinder cone?
Yeah.
Okay.
1959 eruption of Kilauea volcano. The lava was fountaining as high as 1,900 feet in the air. When the molten lava went up that high, the trade winds, like today, blew it out of the fountain and then blew it here in a shadow that goes on for another couple of miles this way, a decreasing depth of this tephra. So we have 9 feet of new rock over this area that came down 50 years ago. This hasn't been shaped by life yet. As you go higher, the weather, the water, and the life have begun to operate on the rock and make it into really a soil that's shaped by the interaction of climate and organisms and the rock itself. The eruption 300 years ago made a deposit of tephra very much like the one we saw that was 50 years old in the other place. But of course, it's had 250 years more for a forest to develop. And if you look up, you can see that the canopy's kind of open here. Once you have a complete plant cover, of course, the soil can't heat up as much as it did in the other place, and the environment is ameliorated, and it's good for all kinds of life. This soil here is some tens of thousands of years old. So compared to what we were seeing yesterday, which was a few hundred years old, at the oldest of the ones we saw, it's had tens of thousands of years for the rock to break down, the minerals to come out, to become available to plants, for nitrogen to be accumulated from the atmosphere. And at this point, we have this extraordinarily rich soil that can support any kind of plant growth in abundance.
This lava that I'm digging into now is about 350,000 years old. And you can see how wet the soil is here. Water is moving through the soil and then hitting the rock and then beginning to move down slope. And after 150,000 to 350,000 years, many of the elements have been washed out of the soil because it's so wet here.
Hawaii is the oldest of the high Hawaiian islands. As these islands are impacted by rainfall over long time periods, tremendous amount of erosion that goes on.
Oh my gosh, look at that root mat.
We've got about 6 inches here of organic mat with roots just all through it.
Yeah, I mean, I think it just indicates how nutrient poor this forest is. We're out 4 million years. The plants are really poor in nutrients, so they're putting roots through the area of the decomposing organic matter, trying to get at whatever is released when it decomposes.
One of the fundamental end products of the long-term weathering of soils is an accumulation of clays. And these clays are very, very small. And so as more and more of the clays pack in there, then the ability of that water to move through the soil becomes more and more limited. So if there's any slope to the land at all, which there is on almost all these lava flows, then the water is going to start to move laterally. And as it moves laterally, then it will tend to drive more erosion. And it tends to create fairly narrow, steep canyons, and then over time, the canyons widen by the walls falling in. And so as one moves across the Hawaiian Islands and you're getting to older and older volcanoes, those volcanoes are becoming more and more eroded as time goes on. And that's partly just a function of the time that rain has been falling on them, but it's also driven by this internal change or development in the soil structure and processes that are going on.
Soils have parents just like we have parents. So they came from somewhere. And soils form from some material that's in a particular location. So in this location, we had wind-blown sediments that came in, and you have these loose sediments that are mostly silt-sized particles called loess, L-O-E-S-S, with some clay and some sand, and then soil formed. That kind of material is transported. It's transported permaterial because it came in by the wind. Other types of permaterial can come in by the water. You can have rivers that overflow, like along the Mississippi. They deposit alluvium. Water rushes out of a mountain range. It might drop a lot of material, like in an alluvial fan. When they deposit that material, new soils form in that material. And then we also have glacially transported materials, soils that formed in glacial sediment. When those glaciers melt, they drop the material. We also have soils that are not transported. We have soils that form in place. Right where we're standing now, we're on a butte, kind of an old mountain range. This particular mountain, the soils formed from rock in place. It was exposed. After probably 1 million years, we had a soil that actually formed in that rock. And the easiest way to see this is you can go to Europe. I saw this castle and it was, like 300 years old. It was stone, and at the surface, you could see a couple inches of soil that had formed. Those kinds of soils take a very long time to form. So transported soils, rough to say, I'm guessing 75% of our soils formed in transported parent material, and then another 25% formed in soils that are in place. A lot of those are up in the mountains.
There's an incredible diversity of soils on the planet. There's not just one kind of good dirt. If you go to different climates, you'll find very different kinds of soils and consequently different kinds of plant communities that are adapted to growing on those soils.
A lot of people look at a forest and think, oh wow, forest soil is the most productive in the world. Most of their organic matter is in the standing vegetation. It's not in the soil. Prairie soil is the most productive. It's that vegetation, the grasses that have these deep fibrous roots, and they're constantly sloughing, dying off, putting more organic matter in the soil. That's what you have here. They make the most productive soils. Because of the prairie soil formation, they have really good structure. Water can infiltrate easily from the surface down into the soil. They store water well in most cases. In the world, maybe 7% of the landscape across the world is in malazols. In the United States, we have about 22.5%. So we have more, we have 3 times our fair share. Alphazols, they may be, in general, the second most productive order. In the world, there's probably 12%. In the United States, lucked out, we have 18, 19%, 17% alphazols. So we have more than our average. Well, if we have 22.5% mollisols in the U.S. and another 18% alphazols, well, 40% of our soils are the two best orders. That's incredible.
Soil is the interface between biology and geology. It's sort of the living skin of the earth.
We're in the Palouse and we're in a wheat field, and most people would think we're on top of a soil, and this is what most people see in soil. They walk on it, but if you look more closely and you look beneath me, we have 30, 40 inches of today's soil that's being farmed over 30 inches of a prehistoric soil, over another 30 inches of prehistoric soil, and it just keeps going down.
As I stand on a piece of land, it's easy for me to forget that the soil under my feet is only 50% solid. 50% of that soil is actually empty spaces, the soil pores that are filled with air, water vapor, and a small amount of liquid water. It is within these spaces that living organisms actually thrive. It is this small fraction that keeps nutrients flowing, regulates and drives the functioning of the soil, and therefore the functioning of the whole ecosystem.
It's Times Square on New Year's Eve all the time in the soil. When you take that soil and you put it under a microscope and you start looking at it, it's a place full of life.
There's so many microorganisms in 1 gram of soil that 70 to 80% of them still have never been identified. So literally you have soil is more properly viewed as sort of like this ecosystem. It's a living thing.
Carbon dioxide in the air is captured by plants. And using the power of sunlight, this carbon dioxide is transformed into carbohydrates by the process called photosynthesis. Once carbon is fixed into carbohydrates, it is available to become the many molecules that feed and form the living organisms of the soil.
When you're looking at the above ground part of the plant that most people see and the roots down into the soil, that plant is putting out foods. Every bit of the surface of that plant is pouring out foods to feed the proper sets of microorganisms in the balances that the plant requires. So it's putting out what's called in the scientific world exudates. The fruit, the blossoms, all of the surface leaves, bark, stems, everything on that plant is putting out an exudate for the purpose of growing bacteria and fungi. And that's really the only reason the plant's putting those foods out. Down in the root system, all of the roots, the structural roots, the lateral roots, the root hairs, the fine roots, they're all putting out foods to feed the bacteria and fungi. And of course, if a plant was putting out food that would feed a disease-causing organism, the plant would be dead. So when this plant growing its roots through the soil starts pumping out all this food, the bacteria grow, the fungi grow, and we have now 1 million bacteria per teaspoon of soil around that root system. We have, miles and miles and miles of fungal hyphae around the root system. So we've got a castle wall. We're protecting. And if the plant's doing that, how's it doing it? Through the exudates, through the foods that it's putting out. Simple sugars, protein, and then carbohydrate. What is that a recipe for? Cakes and cookies. So your plant is dumping cakes and cookies all over its surface, every single surface, putting out cakes and cookies to feed these bacteria and fungi so they grow to really high numbers and are protecting that root system from all of the diseases that would be trying to come in. So in a healthy soil that has the proper set of biology, that plant is going to be able to grow everything it needs to grow to protect that root. And of course, then if we've got all these bacteria and fungi growing, here come the predators of the bacteria and fungi. And when a protozoan eats a bacterium, it releases nutrients in a now plant-available form. They release nitrogen, phosphorus, sulfur, magnesium, calcium, iron, zinc, copper, you name it, the whole list of nutrients that your plant requires. They release those nutrients in a plant-available form, as long as we maintain that biology in the soil.
This is one part of a massive oxidation reduction cycle. And so you reduce the carbon from the atmosphere via photosynthesis, and then that carbon is released back to the atmosphere by oxidation. And most of that oxidation is driven by microorganisms that reside within the soil. And so the soil is the zone in which most organic material that's produced by photosynthesis is then broken down again, and the components are being released. So carbon dioxide is being released back to the atmosphere. Nutrients are being released back into the biological cycle to be used again.
Phosphorus is a nutrient that can only be found in rocks, in the lithosphere. The only way we have is either to mine it to great expense and great amounts of energy, or through the work of microbes, especially fungi. Let's look underneath the top layer of litter, which is undecomposed, and then we find the decomposing litter layer, and immediately you find roots. And there is a stone back here that we're going to pull up. Yeah. And against the stone is where fungi are actively mining the nutrients out of the rock. The microbial body of the fungus, called the mycelium, penetrating through the crevices where no plant could ever go, finds that phosphorus atom and pulls it out through the crevices of the soil to the mycorrhizal root tip. Here, the phosphorus is passed onto the plant and then transported through these fine roots The root grows in this very special form, very special shape. It's a little bit like reindeer antlers. This is where the fungi meet the tree. Have a look at the root tips. This is neither plant nor fungus, but the point where fungi and plant find each other and interact in this very intimate relationship. From here, that atom will move through these fine roots into thicker and thicker and thicker roots until it joins the secondary roots and it reaches into the stream of sap that is pulling those nutrients up through the trunk and into the canopy where the leaves need these nutrients. More than 90% of land plants have mycorrhizae of one kind or another. So it is the rule. There would have been no colonization of the land from the ocean without mycorrhizae, without fungi. Many of these fungi produce a fruit body, something we call a mushroom. Nitrogen is a very important element. The green color of the plants, the red color of our blood, are signs of our nitrogen content. And yet, nitrogen is not easy to come by. Nitrogen is available in the air. More than 70% of the actual atmosphere that we breathe is made of nitrogen, but that nitrogen is very stable. So it's difficult to activate to become engaged in the chemistry of life. That activated nitrogen out of the atmosphere is only available when there are very large electric charges or through a very important and unique trick that only a very specific group of bacteria can play. Plants have learned how to establish a relationship with those bacteria in which the plants have provided an environment for the bacteria to grow, and the bacteria are able to take the nitrogen from the atmosphere and turn it into its available form. This all happens inside the roots of certain plants, like these lupins we have here. They are something like a tumor that was induced by the bacteria. The bacteria start talking to the root of the plant. The root of the plant responds by growing around the bacterium and enclosing it inside. The plant then creates an environment where these bacteria can grow and can fix nitrogen. I've taken a nodule out from the plant root and I'm going to slice it to reveal the place where the bacteria are living, where the nitrogen fixation is actually happening. You can see this red color comes from a molecule that is very close to the hemoglobin in our blood. If the activated nitrogen comes in contact with oxygen, it goes back to its inactive form, and it's impossible for the plant to use it. So for nitrogen to become available to the plant world, it has to be processed by the bacteria in the absence of oxygen. And that's the great trick that the plant learned how to do. The peas, the beans, all the legumes have this type of nodule and make it possible for agriculture to take place without the introduction of artificial nitrogen from a fertilizer.
When you look at the real things that we're dealing with on this earth at a molecular cellular level, change is life. So we're in constant change, we're in constant creation. And it's that constant creation that we get to help manage on a farm.
In a way, agriculture is a dance with nature, and it's about timely intervention. It's about understanding the forces of nature, maybe even learning from the forest, which is the world's ultimate ecosystem. And then it's not exactly improving on nature, but it's recognizing that you have to go with the laws, but then if you act decisively at the right moment, you can get a surplus. And in a way, that's what good farming is about. And on this farm, just to take this example, this land is in good heart. It's been farmed organically for 30 years. This is the 5th time round in the rotation. So we grow clover grass, which is what this is, to build fertility. And that is either grazed by our dairy cows or it's cut for silage, which we feed in winter. And then when it reaches the peak of fertility with very high levels of organic matter or humus, we then plough it and we grow a crop of carrots followed by a crop of oats. If we look at this crop now, which we're just not quite ready to harvest, but we're getting there, you've got these carrots, which as you can see, have done reasonably well. For me, what is amazing about this soil is it just feels so alive and so vital.
Think about the fact that Mother Nature is not growing a forest the same way she's growing a grassland or the same way she grows a riparian system. What's so different about what's going on in a wetlands as compared to that high mountain meadow or the most beautiful meadow you've ever seen in your life, highly productive, or that old growth forest soil? It's the biology in the soil. That's what's different. Maybe we need to mimic that system in the crops that we're trying to grow. If you're growing strawberries, what's the system that you should be looking at to determine what should be in my soil in order to grow these strawberries without pesticides or inorganic fertilizers? Where do the strawberries exist out there in the real world? And most people, when you ask them that question, they're gonna, real world? Strawberries grow in the real world? Yes. Where did they come from naturally? Where are they found out in nature? They're old growth understory plant species. So when you're trying to grow a strawberry in sand that has been sterilized, in what way does that possibly mimic that old growth forest soil? So we've got to get that diversity back into our soils. If you want to grow those tomatoes or potatoes or grapes or whatever you're growing, we've got to get that kind of diversity back into the soil.
What you've got out in the field, if you've got a really good biological field going, you should have 50,000 protozoa out there per a unit of soil, a good-sized unit of soil, and each one of those protozoa are eating 10,000 bacteria a day. Each one's eating 10,000 bacteria a day. So what happens when they eat them? Well, they poop them out, so we call it the poop loop. And what happens with the poop is it goes into the field, it becomes a fertilizer, which is your nitrogen reserve out there in the soil. And you should have a nitrogen reserve, like a bank account, of 150 to 200 pounds or 300 pounds of nitrogen per acre, depending on how good your biology is going, which is enough to grow anything with no fertilization.
For most of the 10,000 years of the history of agriculture, nitrogen had been the most important limiting factor to productivity.
The way my grandfather farmed is he'd break up a piece of prairie and he would grow wheat and oats usually, sometimes corn, until the nutrients were depleted. Then he would break up a new piece of prairie. That's not ecological farming. That's sort of slash and burn farming.
It wasn't until the early 20th century that we were able to increase the production and the introduction of nitrogen fertilizers through a process called the Haber-Bosch reaction. Haber and Bosch in Germany were looking for a better explosive during the war and came up with this way of breaking up the bonds of nitrogen in the air and turning that nitrogen into an explosive form that is also a plant available form. So out of the chemistry of war and bombs came out the first synthetic nitrogen fertilizer.
Then what happened was, as the Second World War came to a close and the fertilizers became available on a very inexpensive basis, that was just at the time when there was a limited amount of new prairie to go to. And so it came as the saving grace. And I still remember my father, the first time he started using fertilizer, and he saw the response that he got from that, and he said, we could never farm without fertilizer again.
As we increase the amount of nitrogen input to natural ecosystems, what is the response of the ecosystem itself to that?
I mean, my father, before he started applying fertilizers, he went to our county extension agent, he went to every farmer whose judgment he trusted, and his single question was, is this going to hurt my land?
The use of nitrogen fertilizer removed a limiting factor from the agricultural ecosystem. So, of course, it yielded a very high increase in productivity. But it also produced very high demands on the soil, demands in the form of increased pesticide use, the demand for other nutrients, the demand for very high inputs of water and fossil fuels through all kinds of ways, especially through the mechanization of the agricultural ecosystem. All these elements put together composed a regime that is called the Green Revolution. And the poster children for the Green Revolution were Mexico and India.
As a child, when I used to walk into the fields, I used to feel the soil was so soft and nice. And whenever I came home in the holidays, I found it becoming sick day by day. I didn't know anything can be done without chemicals. My father was one of the pioneers of the Green Revolution. He visited the Ludhiana University, got the new seeds and everything he did according to the book, what the university and the chemical guys had preached. And now here I am trying to undo the wrong done by the Green Revolution. This is the wheat crop which I have been growing since the last 27 years. But as a chemical farmer, I used to have a bumper crop, very nice crops, maybe 2 tons of wheat per acre. But now, the first year I stopped using the chemicals, it went down just to half a ton. What happened was that the soil was sick. It was waterlogged, it was compact due to heavy machineries, and I was not replacing the carbon, the biomass which I should have. Weeds were a problem. They used to overshadow all my crop. But this year you'll see the weeds are lower than the wheat. And these weeds are basically, they are wild clover, which are a legume. The legumes are the lungs of the soil. So they catch hold of the free nitrogen and feed it back. Nitrogen is the key to a happy soil and happy plants growing. And nitrogen also breaks down the carbon material which we plow in our fields.
There are 2 very fundamentally different outcomes that agriculture can bring to a soil. It can improve it or degrade it. Agriculture is not necessarily destructive. And the difference depends on how one treats the soil. If you look at the history of many ancient civilizations, they share a common storyline. Farming starts in the valley bottoms next to rivers in the soils that are delivered by the rivers from soils eroded off of upland environments that refreshes the fertility of the valley bottoms very naturally. Year after year, as floods come, it deposits a new layer of silt. The soil is built over time. Those are environments that can sustain agriculture for a long period of time because the soil is refreshed naturally. In a very broad sense, if you look at the history of Western civilization, you can trace it from the original floodplain-based agriculture along the Tigris and Euphrates rivers and the Nile River. And many ancient civilizations began in alluvial environments as river-oriented civilizations. What they found is that they could grow more food on smaller pieces of land and support lots of people, so their population started to grow. And that as populations spread up into upland environments, to the hillsides, the same farming techniques were brought up onto the hillsides. Well, when you plow on any kind of a slope, it gradually pushes material quite literally downhill with each pass of the plow. But it only takes a few centuries to 1,000 years to erode through the soils with plow-based agriculture on hillsides. And Greece sort of plowed through their hillside soils, and then to Rome, and the Romans really loved to plow. They would plow 6 to 9 times a year, depending on the kind of soil. And they quite literally plowed the soil right off Roman heartland over the course of a few centuries, a couple centuries BC to the time that Rome eventually collapsed. Western Europe, parts of which plowed through their hillside soils, and parts of which didn't. And then to North America. The great American push west was fueled, if you will, by the exhaustion of soils on the eastern seaboard as plantations and people spread out west in search of new fertile soils. So one of the fundamental things that happened when the plow came to the plains, whether in Europe or North America, was that by laying the soil bare and exposed for substantial portions of the year, wind and rain were able to actually work erosionally much faster than they were under native vegetation.
When I was a kid growing up, every spring in March, we'd have the spring runoff. The mud and the water used to come down. And boy, I'm telling you, this was back in the days of conventional farming. And all this water from these hilltops and these side hills go right down through the house was just around the corner down there. A wall of water came out of this draw, 3 feet high, hit the back of the house, broke the windows out, and it flooded the house, and they just opened the doors and let the water run through. After about, several hours, it turned to mud. And then the mud would come, fill the cellar full of mud every year. And then I took a bulldozer and I went around the house and I uncovered the house, from the mud. All that came down out of these fields, and this is very, very typical of the whole entire area in these hills. Then it became my turn to farm. There just had to be a better way to do it. The direct seeding, or no-till, what it does is it's like a big compost bed. See, we leave all the standing stubble and the residue in place, except we roll the straw out of the seed row, we put it in the center here. Because it's not disturbed from year to year, you get worm activity going on down here in the straw. You'll see the soil is really granulated at the top, and then as we go down through the profile, you'll see here all the worm holes. And of course the wormhole is full of worm castings. It's very, very good fertilizer. The earthworms aerate the soil, they let the moisture go in, and then they provide channels for the roots to grow, oxygen to flow, and all the organisms, things you can't see, all grow in that area too. We don't plow it, we don't disc it, we don't do anything. We leave it, and it gets deeper and deeper, it's eaten by the organisms and dissolved and turns back into plant food.
We've found when we plow, we actually get an explosion of earthworms if we're plowing in a good green cover crop. You know, and just because when a conventional farmer plows all the time and he loses all his worms, it doesn't mean the plow is killing him. From what I'm seeing, I would believe that probably it's the fact that he's not putting any food down for him that's killing him.
So this piece of ground has just recently been tilled, and there's nothing growing on it right now. So the main process going on in the soil right now would be that decomposition process. So the breakdown of organic compounds in the soil and the release of nutrients. And that's one of the reasons why farmers for thousands of years have tilled the soil, because it stimulates decomposition. And also because the tillage process actually breaks up some soil aggregates and makes some carbon that might have been protected previously more available for the organisms. Carbon is actually the key nutrient that drives the life of organisms in the soil. Soil organisms are desperate for carbon, and the more carbon you add to the soil, the more they like to burn it up.
When you move to an agricultural system, you're removing nutrients from the soil in the form of those harvested plants. Nutrients have to come back into the soil to replenish the soil.
The most important thing that we could do right now is to take seriously what Sir Albert Howard called the law of return. What he meant by that was the best way to enhance and retain the living capacity of the soil and its capacity for self-renewal is to return to the soil all of those things that we use, that we get from the soil.
Now this is how we make a compost. We have all the raw material here. Basically we are creating a body. Straw is the carbon. The 50% of the compost is made of carbon. The 25% we put in green matter. So we try to bring the nitrogen in by putting in the green matter. And 25% we have the dung, may it be the cow dung or the buffalo dung. On every layer, we give, this is a biodynamic inoculation, and this is the rock phosphate. A pinch of lime does not let the nitrogen fly off as ammonia. It's an art of making compost. That stuff, when it decomposes, it becomes into this, and this is, it will take another 20 days, maybe it has been given 2 turnings, and you can look at the rich compost, and it's all greasy. Greasy means these are the byproducts of the microbes which have eaten away, and the more greasy it is, the better. There's a lot of humus in it, and it smells like jungle soil.
So what you're looking at here is about a 20-acre site in which we bring food scraps and other materials from San Francisco, the whole Bay Area, and we compost them into a material that can be used on farms. About 1 million pounds of recycled organic food and recycled organic green waste. Our soils are starving for this organic matter.
I am the sheet mulch queen. So we don't grow plants, we grow soil, and soil grows plants. We actually built up 8 inches of topsoil in about 5 years. And now it's up to 12 inches of topsoil.
The organic matter level in this soil has increased dramatically from about 4 or 5% to over almost 18%. And scientists will tell you this doesn't work, but it does, and you can see it. This soil just goes down and down and down and down and down, deep, rich. Now, it didn't start off like that. If you can take with this soil, which is about the poorest soil in the British Isles, and produce healthy economic crops year after year, decade after decade, with the soil improving every year, then I see no reason why this can't happen anywhere. Like many organic farmers, we were also buying in organically approved inputs.
Absolutely,
chicken manures, rock phosphates, lime, all the other things that many organic farmers, and that's stopped. We don't do anything like that.
But a lot of organic growers still do this. They have an organic version of the conventional mode, if you like. But it's a shortcut to problems, which we found to our cost. And so we've now found that the compost, as well as helping the soil disease problems, has its own nutrient value anyway and has reactivated the soil biology. And so now we're in this rather happy situation of saving money, in fact, because we only use compost, and our only inputs are seeds and compost.
Here we have a forced aerobic compost tea brewer. It's mimicking the motion of the creek and is loaded with aerobic soil biology.
So 70% of our freshwater resources on this planet now are used just for agricultural irrigation. And we're drawing down our freshwater resources all across the planet at an absolutely unsustainable rate.
Now this well is at least more than 150 years old, and we had a water level of 30 feet. That was just 40 years back, I'm saying, 30 feet, and now today the water level, the groundwater is 100 feet. So there's a drop of 70 feet.
In China, for example, where 80% of grain is dependent on irrigation, they're drawing down their groundwater, some places already pumping from 1,000 feet deep. Here in the United States, where the Ogallala Aquifer provides most of the irrigation water for the heartland, that's been drawn down by half since 1960.
In California, big impact, particularly in Southern California, but also in any arid region of the world where we irrigate, is salinization of the soil and applying a lot of water. The water evaporates and leaves behind salts.
The loss of productive agricultural soils due to salinization equals that now of losses due to erosion. And so this is why 10 million hectares of land are being abandoned annually in the world because of salinization.
So we use dripper lines. Dripper lines use vastly less water and less electricity to bring water to your field crops. We planted the lines of broccoli down the outside, and we planted tatsoi, a wonderful Asian green, down the middle. The benefit is, if you're looking at this bed from the top now, you actually can't see the soil, which means the sun isn't reaching the soil. So the soil is staying shaded, it's staying moist, reducing the weed competition, and therefore reducing our labor. It also reduces evaporation, so it means we can water less. We make about 200 to 300 yards of our own compost every year, entirely from materials here on the farm. And that goes into our fields, a couple inches thick in every bedrow. It helps maintain water, moisture in the soil. We have friends and neighbors who are irrigating about 3 or 4 hours of drip per day, and we're doing about 1 hour of drip per week. That's the difference in terms of feeding your soil. That allows us to use 1/10 or 1/20 of the water that some of our neighbors are using in this exact same environment here in California, where we have a dry season, long dry season.
Here, what we see is soil from the Rodale Institute Farming Systems trial. We have 300 milliliters of water that is going to be introduced to 1,000 grams of soil. Here is the simulated rainfall. Okay, do you see that we're having runoff now? And this runoff is actually showing the erosion of the soil particles. And we're going to see somewhat different effect when we have organic soil related to the increased organic matter. You see that there is some runoff occurring, but the runoff is much clearer, and there's more water that is being absorbed into the soil. When we add compost to the organic soil, the loss is less than 100. When we have the mulch and the organic system and compost, there's more water that is being absorbed into the soil. Now you see how clear the water is here. As we improve the soil, we get much less runoff. One of the ways of avoiding catastrophic floods is by improving our soil. Now we are going to take these beakers out, and we're going to show you what's happening below the surface. If we look at the bottom of our containers, we see that actually there's no water that runs through the conventional soil, so that you're not getting anything that could be supplying the aquifers, the water storage that is underground, or the surface rivers because of the poor nature of the soil. But as we use these organic soil methods and we create an organic soil, what we see is that we're getting not only less water loss on the surface, but we're getting water charge in the subsurface, which is feeding our aquifers and our surface streams. So this is very good for our natural resources, and most of our water comes from underground water sources.
So we've watched here at the Rodale Institute over the years is when we have drought years, our organic fields can produce 30 to 70% more corn or more soybeans because there's the organic matter in that soil than a conventional chemical synthetic-based farm ever could. So when they talk about what we need is bioengineered plants for drought resistance, we're kind of slapping our foreheads and going, what? What we need is healthy soil with organic matter in it, and you don't have to put a bioengineered gene into that plant. You can outproduce conventional by a whole bunch by just improving that soil.
Now here we have a new technique called organic no-till, and you can see that the soil is covered with a cover crop that is rolled down. When we put a mat on it, the materials that are in it are high in the nitrogen that is needed for the corn plant. We get both the fertility and better resource conservation.
In my gardens, I grow two things all the time. 50% for people, which is the potato in this case, and 50% of the land for nature, the soil improvement cycling crops. It's very important. Without a balance between the two, things will collapse. In my gardens and in the gardens of the future, I believe, we need to recognize and feed nature as we feed humanity. And so I grow this crop of mixed soil improvement plants. You can call them weeds. They're mustards and vetches and clovers and a wide range of different plants in here, and as well as potatoes. There are no bugs, there are no disorders of any kind out here. It all transpires. And the potato plant has not yet come to bloom, and it's an immature potato plant at this time of year, but we'll harvest one just to examine what it looks like. We see large masses of fibrous root systems, and we see nice, soft, crumbly soils that have good aggregation to them, held together by yeasts and molds and bacterial colonies filled with fibrous small root systems. And there's the mother potato, and it's just beginning to fruit, and it has a few small new potatoes. And it weighed about 2.5 or 3 ounces, and it's still solid. It has yet to be drained. It's just barely begun. Generally, under this circumstance, I will plant 1 potato in this garden, under the way I garden. I'll plant 1 potato, and I will get 14 equal-sized potatoes. This is also part of nature. Humanly trained, I'm afraid. Well, that's the end of the potato story.
In the U.S., there's 100 million head of cattle that are grazing the land, 7 million sheep, and 4 million horses. And the U.S. Department of Agriculture reports that we have a serious overgrazing problem. And of course, that contributes to increased soil erosion. Not as bad as Africa, where they've almost totally stripped all the grass off the land.
About 5 years ago, we certified our cattle as organic. And in doing so, we stopped any inputs, of course, to the soil and to the plants, but we also stopped using parasiticides or any antibiotics. And we were walking around, and I remember 2 or 3 years ago, we looked at some cow patties, and we noticed some holes in the cow patties. And I remember talking to my sister, Ginny, saying, do you remember when we were growing up, we'd see cow patties, and they'd be filled with holes, and then the cow patty would disappear. I said, they're back. Whatever's doing that, it's doing it again. The parasiticides that we give to the cows come out very concentrated in their manure. It ended up killing the natural dung beetle that was here. And it didn't kill them all. They just started to recover when we stopped using those parasiticides. With the dung beetles, they'll take little packets, and they make little balls, and they'll carry it up to 4 feet away from that dung pile. So what you're actually doing is spreading the fertility around, aerating the soil, and they're doing their job. Because the cow patty, if we don't have the dung beetle and they don't move, you end up with a burned hole in the grass from the high nitrogen content of the manure and the shading. And as it decomposes, that's where the increasers come. That's where we end up having thistles and weed problems. So, truth be known, we've actually had a reduction in weed problems after certifying organic. We've also had an increase in productivity because the soils are healthier, the microbes and the critters in the soil coming back to life. Properly managed grazing is the best thing that can happen to our California grasslands.
For millennia, animals have been part of agriculture, and that's because they're an important part of our diet, but also they're a unique way of breaking down organic matter, breaking down plants, and returning them to the soil in a way that feeds the microorganisms in the soil so that they can keep making those minerals in that cycle available to the next plants that are growing.
In traditional agriculture, animals were an integral part of the farm because they returned nutrients, especially nitrogen, into the soil in their manure. But as we moved into industrial agriculture and removed those animals, we created 2 problems. Large accumulations of manure, which means a lot of nitrogen in the wrong place, and soils that were depleted of their nutrients, so that we now have farmers who are dependent on synthetic fertilizer.
About half of the fertilizer that we add, half of the nitrogen fertilizer is lost from the system right away, and about half is taken up by the crop. And that's the average. It can be much higher. In vegetable systems, you can end up losing 80% of the nitrogen.
Small amounts of nitrogen are continuously brought into an ecosystem by bacteria, which fix the nitrogen from the air into a plant-available form. In organic farming, leguminous cover crops and manure add nitrogen to the soil. There is minimum leakage of nitrogen in these organic farming ecosystems because the nitrogen is released slowly, and most of it is taken up again by living organisms. When synthetic nitrogen fertilizer is introduced into a field, plants can use it to produce more biomass, and for a farmer this represents higher yield. But plants can only use a limited amount of that nitrogen fertilizer. So some farmers use more and more fertilizer to get smaller and smaller increases in yield. Excess nitrogen is released into the ecosystem, and forms of this nitrogen go into the air as potent greenhouse gases. Fertilizing nitrogen also leaks into the soil and into the water system, creating a range of problems from nitrates in drinking water to the eutrophication of waterways and ultimately dead zones in the ocean.
You end up with a lot of extra nutrients in those waters, and that causes algae to bloom, the plankton take off, then they die, they sink down to the bottom. And while they're decomposing, the oxygen demand goes up. So all of a sudden, where there was oxygen to support fish, shrimp, other shellfish, there isn't any, so they all die. Then you've got even more dead organic biomass to decompose. In the Gulf Dead Zone, the average size for the last few years has been about 7,000 square miles, about the size of the state of New Jersey. There is one dead zone, the one in the Black Sea, which was the largest dead zone in the world, that disappeared for about 10 years because when the Soviet Union collapsed, they could no longer afford fertilizers. So that's promising. It means that we can do something about it if we change our practices. The strategy that we need to use is to look at improving our field efficiency, and this has implication for greenhouse gases, including carbon dioxide production, because this synthetic nitrogen that we're using is extremely costly in terms of energy, which means it produces a lot of carbon dioxide. This accounts for about 50% of the energy use in agriculture. So if we're continuing to just use it at a 50% efficiency, we have the environmental consequences of the leakiness and also of the energy use and all the pollution that occurs from manufacturing it. One strategy that has a huge impact is to just modify rotations so that you have cover crops alternating with the cash crops. And we conducted a study of all the research that's been done looking at cover crops, and we found that on the average, if you introduce cover crops into an annual rotation like corn and soybeans, you reduce nitrate leaching by 70%. So that's a huge reduction.
A healthy soil is the fundamental part of a healthy grapevine. Of course, the fundamental of healthy soil is adding organic matter to the soil. So if we came out here in February or March, we'd be up to our chest in peas, oats, vetches, cover crops that we've grown to add organic matter back to the soil, along with the compost that we make from our grape pumice. And here's a nice earthworm, and we can just see this is like chocolate cake, basically. And this just smells so good. This is going to provide all that this grapevine needs now to provide great grapes with deep flavor. Well, you know, we came out here and into another vineyard in the Napa Valley, but there's really something fundamentally different about this vineyard is that the The soil itself really doesn't have a lot to contribute to this grapevine or to these eventual grapes. And the reason is they've not added organic matter back to the soil, and therefore, as you can see, it's become hard and compacted, so it's really become dirt, not soil.
We started this farm back in 1974. One of the things they told us was that we wouldn't really be able to farm organically in California because California is an arid climate. I mean, even here on the coast, we have a lot of rain. We have 30 inches of rain annually, but it all occurs in a matter of 4 months. So we have a long period of arid conditions, and we were told that probably you weren't going to be able to farm organically in any commercially successful way because you couldn't get the humus levels high enough to have the bacteria in the soil hold the nitrogen and the fertility elements that it needed for the crops. It hasn't been difficult. In the early years, we would do really what we're doing now. In the fall, we plant cover crops. In the spring, we plow those down and then start planting and put out compost. And in fact, we're farming organically all over the state now. And this farm is the oldest certified organic farm in California.
Once we changed and we started to compost our livestock manure and put that back on the soil, we used green manure cover crops and incorporated that biomass back into the soil. Within 3 years, and even our neighbors who would walk across the field saying, yeah, your soil is so spongy. Now, what did you do? And it was that living, that return of the life of the soil. Within 2 to 3 years, you can make a tremendous difference in soil, honoring that law of return.
For 28 years, this area has received conventional agriculture. And one of the things that you'll see here is that the corn is actually spindly and yellow, and this is related to the soil has not improved during the experiment. This comes from long-term organic management. One of the things is that people would freak out with these weeds because they would say that they're taking away from the crop. But our long-term data shows that we can produce even more in these organic systems than in the conventional systems. So that, like a lot of this has to do with how you view things. Can you let life live?
One herbicide that was really touted was glyphosate. The trade name is Roundup. The testing that they did before the product came on the market was only on the active ingredient itself, not on the actual formulated product. Not only does glyphosate destroy mycorrhizae in the soil, they can actually decrease levels of beneficial soil microorganisms and increase the level of harmful ones. Over 95% of the soybeans in the U.S. are genetically engineered. What is that trait that is engineered into them? They're called Roundup Ready soybeans. They're designed to be used with Roundup.
So where we've gone in and destroyed the biology in the soil, we have to be putting on inorganic fertilizers. We have to use pesticides. We're going to have weeds. So it becomes this downward chemical cycle.
There's over 10,000 agrochemicals that have been registered for use in agricultural production systems. So what we have is a deadly cocktail that has developed.
Over 1.1 billion pounds of pesticides worth $25 billion are used each year, much of it ending up in soil and water.
U.S. companies have submitted applications to the EPA to get approval for corn that is engineered to be resistant to 2,4-D. which has been linked to non-Hodgkin's lymphoma. 2,4-D is an herbicide that was in Agent Orange.
Atrazine is an herbicide that is used to control weeds in crops. In the case of atrazine and nitrate, especially those two mixed together, nitrates shut off your defenses to your body against toxic chemicals, and so it's like tying your hands behind your back. We found that common lawn chemical mixtures at very low concentrations can induce abortions and resorptions of fetuses. This is something that was not expected, but the greatest interest here is that the greatest effects were at the lowest doses, not the highest doses. Fetuses are exquisitely sensitive to very small concentrations of chemicals. These chemicals can completely alter developmental trajectories. Abundance of nitrate and atrazine is associated with human birth defects, baby male genitalia problems, learning abilities in terms of math skills and in terms of language skills. Kids who are conceived in these months when these pesticide concentrations in water are high have higher probabilities of all these kinds of developmental problems and fertility problems.
Everything we are is made of the soil. The food we eat is a produce of the soil. If we have declared a war against the soil itself, if we ensure that the fertility through which the human species can continue is robbed from the soil, then we are literally committing a species-level suicide.
If this soil is healthy and balanced, this cabbage plant is going to be healthy and balanced. The corn plant will be healthy, so that when we eat the crops, we're going to be healthy.
And what I'm seeing with this farm, and by tending this farm, and the soil here is very, very healthy, you end up getting this whole food web.
How do the various species and organisms within a system interact with each other and benefit from each other? And how can you then, in agriculture, organize those in a way that you get those synergies, those benefits from the synergies? One of the really exciting things here is that we have this working relationship between the farmers and the chefs in the restaurant.
Well, there's something really special about working with passionate chefs.
To get that good carrot, you've got to have good ecology behind the carrot. It's grown in the right soil, it has the right amendments in the soil, it was picked at the right moment, all of these issues that improve your overall local ecology, because generally if that carrot's so delicious, it's locally grown.
Blue Hill Restaurant here is well recognized now, not only throughout the community, but throughout the country and even to some extent throughout the world, as that's where you're going to have the best meal of your life.
And as those meals go out, occasionally catch a taste and just see the presentation, what he's trying to get across, which is really just trying to get across this awareness of relation to the food.
I think the answers are on these little microbiological levels, literally, because it translates, for me, going back to flavor. And you cannot have good flavor without that kind of attention to detail and knowledge of the biology and knowledge of the chemistry, knowledge of these interactions that are going on a soil level that are key to health and to flavor.
And that to me is hugely inspiring.
The best economic returns are from the best vegetables and fruits and even meats that are grown in the right way.
So here we do not bring any outside inputs for either our livestock or our horticulture operations. Everything that's used here and all of the waste that's produced here gets composted and put back into the system.
Just like the carrot is not the carrot is not the carrot, compost is not compost is not compost. You know, I thought if you make compost, right? I mean, but there's a recipe to that that's as interesting and as profound and as important as the recipes that I'm making in the kitchen. And if you have the biology right, you're going to taste these different levels of flavor.
The success that we've had in our food system over the last 70 years or so has been due to a unique convergence of circumstances. One is this incredible supply of cheap energy in the form of oil and natural gas and coal.
We saw in the UK in the year 2000 when the lorry drivers went on strike and there were no lorries moving and there was no fuel, liquid fuels, we came about a day and a half away from a major food crisis in this country because it came very clear that we had no food resilience to fall back on.
So the real question is, what kind of food system are we going to transition to when we no longer have these cheap fossil fuels that provide the fertilizer and the equipment and everything else that's made these highly specialized productive systems possible? People think, well, it's not going to be such a big problem because there's alternative energy. So all we got to do is switch from Mideast oil to corn-based ethanol from Iowa, and then, you know, problem solved.
Biofuels in the United States are being produced with corn. 99.9% are with corn. Corn production in the U.S. causes more soil erosion than any other crop grown in the nation, number one. Number two, corn production uses more nitrogen fertilizer than any other crop grown in the nation. And the leakage of the nitrogen goes down the Mississippi, and the National Academy of Sciences indicate that corn production is the prime cause of the dead zone down in the Gulf of Mexico. Another, corn production uses more insecticides, more herbicides than any other crop grown in the nation. Because it takes 40% more fossil energy to produce that gallon of ethanol, that means that there's significant contribution to the global warming or carbon dioxide because of the excess fossil energy used. Oh, I should mention the water. It takes 1,700 gallons of water to produce 1 gallon of ethanol.
A very inconvenient side effect that could happen from a very aggressive move towards biofuels is that if we grow the crops that would provide those fuels in ways that are as erosive as conventional agriculture is now for growing corn, say, we could be in a situation where we're essentially trading a system that mines oil for a system that mines soil, in which case we've just changed the time frame over which we're going to engineer a disaster.
We didn't ask the question, as we use more land and put pressure on more farmers to produce more corn, to both provide for the feed and for the fuel, and on top of that, the exports, where are we going to get the additional land from? We sort of kidded ourselves into believing that, well, we could just increase the yields rapidly enough so we don't have to worry about more land, and of course, that hasn't worked that way.
I think what happened in science, and I come from a science background, is we became too reductionistic and we started to look at things too narrowly. And what the healthy soil conversation is about is really about the whole biological system. And rarely do we investigate things as a system.
In 1984, there was a drought in the south, and lots of animals were dying, and there was migration. So I studied the region, and I found the rain hadn't reduced. So why was there a drought when the rain was the same? And it turned out that new seeds had been brought that reduced the plant height, got rid of the straw. There was no straw for the soil. There was no straw for the fodder for animals. So your rainfall was the same, but you had a soil drought because your organic matter had not returned. You had a fodder drought because you had now redesigned, in this case the sorghum, to produce more grain for the market at the cost of less organic matter for the soil and for animals.
%60 of our ecological systems now are reaching the point of collapse. If that were to happen, then it will fundamentally change the functioning of the planet. Now, I don't know if everybody grasps the meaning of fundamentally changing the functions of the planet, but that really means that the planet could evolve into a kind of climate that's not very good for us as a human species. How do we continue to produce an adequate amount of food for a population of 6.5 billion people and getting larger? We have increasing energy costs, depleting water resources, and more unstable climates and more severe weather events. They have to be addressed in terms of fundamentally changing the way in which we produce our food, which makes it more resilient. And the only thing that I can see that really looks promising is to get back to the fundamentals of the soil.
We can sequester over 3 tons of carbon dioxide per acre with organic regenerative methods, whereas conventional chemical-based agriculture emits carbon dioxide.
So we would solve so many problems if we would just get the biology back into the soil, stop killing it.
When the colonialists came here in New England, this became a key area to produce food for the Burlington area. In the middle of the 20th century, we began to see the transformation of agriculture so that local food production began to move further and further away. Those farms essentially became difficult to stay in business as they competed with food from around the planet. And when we got here, which was 30 years ago, there was one farm left, the last dairy in Burlington, run by a 90-plus-year-old woman, and she was just hanging on. We started to take on the restoration of this floodplain, which had become really a dumping ground for the city of Burlington. And we saw this as just an exciting opportunity to imagine the transformation of the food system, which was what our business was about, producing local food in your garden. This is a floodplain, sandy soil. We had lost almost all the organic matter in the soil. So one of the things we could do is we could take all the waste from the community in terms of food waste and yard waste, and instead of taking it to dump, we could put it into a compost project. That compost has brought the fertility back up to 4 or 5% organic matter in the soil. That then gave us the capacity to incubate and create the farms that are down here now. 0.1% of the food eaten in Burlington was coming from Burlington, and we had a goal of could it become 10% of the fresh food. We're in Vermont, it's cold, so you can't do it all year, but we're getting awfully close to 10% of Burlington's fresh food that's consumed here now being produced here in the Intervale. There are now 13 farms down here. They share greenhouses, they share tractors, they share irrigation. They are now sharing refrigeration. They are sharing distribution, so we have a food hub that actually aggregates their available excess supply and gets it out efficiently into the community. We actually have about a dozen employers who have supported the idea of a CSA where we actually are distributing weekly to their employees. We deliver right to their places of employment. So the employers began to realize the value of local food, health, and connecting their employees to the local food system. This is not just happening in Vermont. It's happening
all over the country. So we have people knocking on our door saying, could we do this in our community? The simplest answer is make sure you've got fertile soil, and if you don't, figure out how to get there and get it accessible so that it's not too expensive for people to farm. Make sure that you can support young people to be able to be successful at farming, and make sure that the market is there so that they can make a good living. You put those things together in a dynamic, interrelated way where policy plays a role, but ultimately it's the economic system that is that which is driving, I think, our future success. One of the things that works here, and in many old cities you have that same situation, is a forgotten bunch of land next to rivers that actually are fairly fertile and could be brought back to life. And sort of the integration of people to agriculture is a lot of what this new food system is about.
One seed you plant, you get 1,000. 1,000 seeds you plant, you get 1,000,000. Fertility really is the power of the soil to keep producing, the power of the seed to keep reproducing year after year after year.
Harchikaku gadwaluku ukudu kandali gol gafa banyaranda thajin gadwali harchikaku gadwaluku ukudu kandali.
It was called the IAASTD, the International Assessment for the Role of Agricultural Science, Knowledge, and Technology in Development. And it was basically, what's the answer for world agriculture? And after a 4-year process, in 2008, the final report came out, and they basically said that the answer is not high-tech, it's genetic engineering is not going to save agriculture, neither is nanotechnology or these high-tech solutions, but the answer is these more ecologically rational agroecology.
The question is, can organic, sustainable agroecology feed the world? Sure it can. And I know this because I was involved myself in a lot of research in Africa. We have quadrupled, up to even 10 times more yield, totally sustainable, organic actually, by doing the right thing and by building soil. So the yields go up year after year to reach levels which, if every African farmer, let's say, would produce according to some of those systems, there will be plenty of food around for everybody. But, there's a but here too, it doesn't fill the pockets of a few business people. This helps the farmer and the consumer. And we have to widen this stem to make sure that there's more connections from farm to consumer and also more people in between. It's important because agriculture needs input-output no matter what you do.
Yeah, once a week we do a box of food that's got 6 and 10
And you can imagine sort of two possible alternative futures. If we continue to aggressively pursue plow-based conventional agriculture the way that we are at present, we'll eventually deplete the supply of soil. Eventually, the areas of highly fertile, highly productive agricultural soils will become very valuable and fought over. They will become sort of the central organizing element of the geopolitical reality. Why? Well, because soil is the fundamental resource. On the other hand, agricultural techniques like intensive organic agriculture and no-till that can produce large crops of food without depleting the soil, and in many cases actually improving soil quality, it would encourage sort of small-scale, labor-intensive organic farms that would supply what's coming to be known as the local food movement. Two very different futures, both of them totally possible, and the mechanisms that may guide us towards one or the other are going to evolve from what consumers choose to do with their food dollars and what governments tend to encourage, subsidize, and or penalize or regulate. The future's wide open.
Back in the 1960s, the chemical companies tried to sell the idea that chemistry was better than life forces, and they called this better living through chemistry. But now through science, we understand that there's lots of side effects from the chemical approaches to food and agriculture. So we call this better living through biology.
When you go to this system, the soil returns to what it was like when it was first broken out. You know, you go out there and you start digging in that, and that's just an awesome thing, you know.
In the original Hebrew, Adam is the masculine form of the Hebrew word Adamah. Adamah is soil. So Adam literally means earthling, and as described in the 2nd chapter of Genesis, Adam is fashioned by God out of Adamah, out of the earth. The translation is the dust of the earth, but it's really the afar, the material of the soil. And now the question is Adam's mate. In Hebrew, Chava, or in English rendered Eve. Chava means literally life or life giver. So together the combination of Adam and Eve mean quite literally soil and life. Perceiving that life is associated with the soil. Adam and Eve are placed in the Garden of Eden, which means literally the Garden of Delight, which is nature, and given an assignment. Not mastery, but a role, a task, to serve and preserve. It says in Hebrew, le'ovda u'leshamra. The King James translation says to dress it and keep it. But my translation is to serve it and to preserve it. We banish ourselves from the Garden of Eden by despoiling it. And when mothers see their children playing in the soil now, they say, oh, that's dirty, and they rapidly, quickly wash their hands of the dirt. And we misapply that terrible word dirt to soil, which is the fount of all cleanliness, by the way.
Something in here.
Think of all the many generations of people in past generations who've died of all manner of disease, and somehow the soil cleanses them all and recycles their bodies into the materials of life.